Okay, so here's what we're doing. We're trying to develop the idea of torque. So torque is what causes angular acceleration, right? So it's the rotational version of force, right? So just like force leads to acceleration, torque leads to angular acceleration. And we took as our kind of test system for our development a system that you guys use all the time, every day, a door. So here's a door. I drew it from the top view. Here's the hinge. And we took a look briefly at several strategies for opening a door. Most people take this approach, right? They push on the door like this. They push at the end where the door handle is. They push it in this way. They angularly accelerate the door from rest. That's how you get the door out of your way and exit a room. It is also possible to push on a door like this and open it. Although, as you guys probably know, the closer you are to the hinge, the more difficult it gets, right? So sometimes you hit a door, maybe you try to push it and you don't realize the hinge is on the other side and you have a lot harder time because you're so close to the hinge, right? Has anyone ever had this experience? Okay, not just me? All right. And it's also possible to mess up in other ways. If you pull on the door handle like this, outward from the hinge, nothing will happen. So no matter how hard you pull, you will never achieve anything happening to the door. No angular acceleration means no torque. Maybe you'll rip it out of the hinges by accident, but the door is not opening otherwise. So we need to consider force and its location and its orientation. These are all things that are going to matter when you're trying to actually angularly accelerate something. So I'm going to take a first stab at a formula for torque. Let me just talk about the magnitude of it. We'll add the direction later. That's trivial. And my first guess is going to be R times F. So what R is the distance from the pivot, or the hinge, to the force application point. You might want to more informally refer to it as leverage. So what you do is you measure how far are you actually exerting your force from the hinge. I can, for instance, draw in this right here would be the leverage of that force, right? That's how far it's applied from the hinge. And then these other two forces have the same leverage. They're both applied at the other end of the door, so the leverage would be the whole width of the door. So let me explain to you why it is that I chose to multiply them for my guess. The reason, of course, is that you can get more torque either by exerting more force, or obviously only have so much force you can exert. Your other option is to apply it further from the hinge, right? So if either you exert more force or you apply it further from the hinge, then your torque is larger, right? So those are the two options you have. So for instance, if you're trying to loosen a rusty bolt with your hand and you can't get it, then you go and get a wrench. What does that do for you? It doesn't make you stronger. It does allow you to, though, to apply your force at a larger distance from the pivot. Get more leverage and you might get enough torque to get it loosened, right? And what happens if you R is 0? No torque. You can't open a door by pushing on the hinge. Try it. You won't get anywhere. You have to apply some distance from the hinge. Now, this is not only a good first guess, it's enough to get the units of torque. So the units of torque, what's units of R going to be? Even SI meters, right? How about force? Newtons. So the units of torque are meters times newtons. Normally, you don't write it that way because that can really easily be mistaken for a millinewton. It's not a millinewton, it's a meters newtons. So for that reason, we oftentimes reverse them, because then you can't mistake the M for a prefix. Newton meter, right? Now, you might recall that a Newton meter is also a joule, but we don't call this a joule, okay? Now, the fact that it came out to be the units of joule is not a coincidence, but it's not really important to get into why that is. But we don't call it a joule, okay? This is not a work. This is not an energy. This is not even a scalar. It's, in fact, it's going to be a vector. It's going to be the rotational analog to force. And since force is a vector, so is torque, okay? So we call it a Newton meter. In the English system unit, instead of meters, you use feet. And instead of newtons, you use pounds. So foot-pounds is another non-SI unit for torque. And then you don't have to reverse it to pounds-feet because there's no problem with the getting confused with M being a prefix. So you may, for instance, be aware that your car can be rated as having a certain maximum amount of torque, right? Foot-pounds of torque from your engine. So that's a good first guess. It's enough to even get the units. The only problem is that it does not account for all three factors. It accounts for force and location, leverage, but it does not account yet for orientation. And here's how I know that. This last force, this one, it can be a substantial force acting at a substantial distance from the pivot, so R and F can both be big, but I already know that nothing happens. I get no angular acceleration for this. So what does that mean is the torque? Zero. Zero. We have no torque. So right now our formula is flawed because it would seem to suggest that if you exert a large force at a large distance from the pivot, then it should get a large torque, and yet we know that it's not. Well, that's of course because this final factor, orientation, is missing. So let's talk about how we can modify this so that it does have not just two, but all three factors in it. And here's what we do. Let's suppose that hypothetically we have our door like this. A force could be applied in basically any direction. But if we apply a force in a given direction like that, remember that this door is constrained to swing around like that. It can't just move willy-nilly. It is constrained to sweep around the hinge. So if we break this force into components, I'll call this the radial component, and I'll call this the tangential component. And only one of those is actually going to be useful for opening the door. Which one?
Tangential.
Tangential, right? The radial force is just trying to pull it out of the hinge. It's not going to accomplish anything, right? So this, there is no torque due to this. All of the torque is actually that you get is from the tangential component. That's the only thing that can actually cause anything to happen. So as a modification to my formula, I'm going to suggest R times not the total F, but just the useful part of F, F tan. And just like that, I'm basically done, okay? I just have to acknowledge the fact that if there's some part of the force that is of no good to me, it doesn't really bear including in the equation. So we can go back over here and see these two forces. Someone intelligently applied them in such a way that the tangential part of it was all of it, right? Everyone's smart enough to apply their efforts tangentially to the door. Then you don't have any wasted effort. So my first guess was not only a good guess, it's actually completely correct for these, right? Because here, my entire force happens to be tangential. But how much of this force is tangential? None. The force here, the tangential component is 0. I somehow, for some reason, applied all of my force radially, and so it's all wasted. So even though I may have a substantial force, the part of it that's tangential is nothing, right? So that's all waste force. Question?
You're calling it radially because it's not centripetal, so it's just opposite?
Well, I mean, it could be radially inward or radially outward. So centripetal is a very specific thing that is used to make sure that something stays in a circle. This we're not going to really have any issues with staying in a circle. It's tied down with a hinge at one end, and it's a solid door, so we assume it doesn't fall apart. And so even if this radial force is not right for centripetal, it doesn't matter, right? Because there are already internal forces, intermolecular forces that are providing the centripetal force. So this could be any amount at all, and it's waste force regardless, right? And I call it radial because it's radial to the circle that you move on, right? You can only move along the circle, tangential to the circle. You can't move, the door can't be pulled radially inward or outward from that. Are there any other questions? Okay, so from here it's all bells and whistles. This is pretty much in essence correct. The things that you need are how much force, how is it oriented? So the orientation factor is making sure that you only keep the part that's relevant, the tangential part. And then of course the location, that's where it's applied, that's R, that's your leverage. So from here I just want to make a few modifications that, not that they substantively change the ideas, they just make it easier to calculate. So here's what I want to do. I want to include this angle as theta, so then F tan is F sine theta. So let me copy down my final torque formula. My final torque formula equals RF sine theta. And then, remembering it's a vector, this is just going to be the size of it. To make it a vector hat, I'm going to put in a plus or minus in the front. And this is the same ideas from any rotational quantity. The plus is counterclockwise, and the minus you pick if it's going to make the thing go clockwise. So this form is nice for a couple different reasons. First of all of the three things that we said should go into torque are all present. Force, location, and orientation. So R, F, and theta. They're all in there, they all matter. Now, anytime you see someone doing a SOHCAHTOA, like I just did, F sine theta, and trying to make it a permanent part of the equation, you should be skeptical, because of course one person's sine is another person's cosine, right? If I'd broken it up, going up first then over, I would have gotten a cosine here. So, just like the last time we did this, where we did a SOHCAHTOA and worked it permanently into the formula, was the work formula, right? Work equals F delta X cos theta. It was always cos theta, right? But the trade-off is if it's always a cosine or always a sine of the equation, you had better believe there's going to be some very distinct way of picking the angle, so then you can be guaranteed that it's the right thing. So there is a very specific way of picking this theta, and let me show you what it is. If you identify theta in this way, it's always sine in the equation, never cosine. Here's what you do. So if you have I keep on picking on the door here. If you have a system like this, you know the pivot, you know the force. What you do to get the angle is you draw a line, a radial line, from the pivot through the force application point like this. Okay, so let me write down this prescription. So draw a radial line from the pivot through the force application point. Then, the theta that you seek, the theta that you want to plug into the equation, is the angle is between that line and F. That's the prescription for finding the theta. So it's almost harder to write down in sentence form what to do is to just show you. So I just drew a dotted line from the pivot through the point, this is the point where the force was acting, and I want to measure this angle. The angle between that force vector and that line. Now you might say, why not this angle? Isn't that also satisfy the prescription? Isn't that also an angle between that line and the force vector? Sure, go ahead, knock yourself out. Either one will do. They'll give the same answer. This is a property of sine that you can use to your advantage. It turns out the sine of an angle and the sine of its supplement, is that the right word? When two angles add up to 180?
Yes.
Yeah, okay. It turns out the sine of an angle and the sine of its supplement is the same value anyway. You can't go wrong. Okay, makes your life easy. So, let's try it out. First of all, hopefully it convinced you that this angle that I just identified, at least the first one, is this angle, right? If I drew this line out here, that's the angle I just identified. Let's take it out for a spin and try it out. Let's say we have something like this. So I draw a line out from the pivot through the point where the force is applied. What theta should I use? 90. So I get torque equals RF sine of 90. What's sine of 90? Nope. 1. So there I get maximum benefit, right? All of my force is helpful, right? All of my force is tangential. So all of it counts in the torque. All of it's along the circle, right? Let's do another one. Let's say I'm just pushing the door inward like this. Okay? So let me draw a dotted line from the pivot through the force application point. What angle should I use now? 180 or 0, doesn't matter. Torque equals RF sine of 0 or 180. What's sine of 0 or 180? 0. So now I get torque is nothing, which makes sense, right? Because this is all wasted force. You might crush the hinge, but you're never going to open the door, right? I will have you mostly do these two cases, okay? So one of the things that we got to save some fun for physical calculus. Mostly, you will have to identify whether all of the force is useful or none of the force is useful. You won't have a kind of mid-case, right? So that's what the sine of theta is there for, right? It's to when some of the force is useful for rotation and some of it is useless, okay? So you should kind of have an idea of what that's for, but most of the time you're going to have to decide if your torque is 0 or R times the entire force, okay? Are there any questions on that before I move forward? Okay, so that's our master torque formula right here. Okay, again, most of the time it's going to go into RF or 0. So that's the formula as a whole. And again, you do still have to take plus or minus depending on if it's counterclockwise or clockwise. So what I want to do now is just start doing a bunch of examples. I'll start conceptual, then I'll go quantitative, and then I'll make the quantitative examples harder and harder. So this is conceptual example number 1. I'm going to have my system be this. This is going to be a top view of a frictionless table. And my system is going to consist of a flat bar that is sitting on a table. You can imagine it like, you know, someone left a ruler on an air hockey table. Okay? So let's try to poke and prod it in various different ways. Remember, this is a top view, so I can poke and prod it from any direction, and it'll be a horizontal force, right? It's always in the horizontal plane. So I can push with various forces in the horizontal plane. You see what I'm trying to explain. So we're not going to have any vertical forces up or down. We're just going to poke and prod it in the horizontal plane. So let me just kind of talk through here. Here's my first case. I'll call this case 1. Case 1, I'm going to apply a force like this and a force like this. They're going to be equal and opposite. And I tried my best to draw those arrows exactly the same length to indicate these forces have the same strength. So first let's talk about the net force. If we have equal and opposite forces, what's the net force? 0. At this stage, we've learned that the net force really only tells us about the center of mass, right? So what that means is that the acceleration of the center of mass is 0, so the center of mass has to stay at rest. When you find out about net force, it tells you what does the center of mass do or not do. And if this is a uniform ruler, we can safely say, of course, the center of mass isn't anywhere counterintuitive. It's just right in the center. For symmetric objects, the center of mass is coincident with the geometric center or midway point. That point can't move. But even though that point can't move, there could still be rotation of the other points around it. So let's take a look. Well, this force seems to want the thing to go clockwise. So what do we call that torque? Is that plus or minus? Minus, right? Minus is clockwise. Torque is minus clockwise. So the rest of the object could still do something. Let's take a look at the other force. This one, noticing I'm tracing around my pivot, my center of mass. The center of mass has to stay put, so if there's going to be any rotation, it's around that. What about that force? Is that torque going to be clockwise or counterclockwise? Oh, did I get them both wrong? Yeah, wait, yeah. Yeah, they're both counterclockwise. What am I talking about? This is plus counterclockwise, and this is plus counterclockwise. So that's interesting. The forces canceled on the force side, the old linear stuff, but they actually agree on which way this thing should rotate. How did that happen? Well, of course, location matters. So even though the forces are in opposite directions, they're also opposite sides of the pivot, which means they actually rotate the thing the same way. So is this going to have a net torque? Do these two cancel, or do they reinforce? Reinforce. What's the net torque going to be? Positive. Positive, right? So this thing is not going to stay put, except for the center of mass. The angular acceleration of the rest of the object will be non-zero. Now this is going to be hard to show on the board because obviously the board is not a horizontal surface. But let me imagine here, I'm going to have to hold this object down so it doesn't fall. But I have one force like this, which tries to rotate it this way, the other force like, one force like this, and the other force like this. They both agree this thing is going to rotate, right? So what I'm really trying to get at here is that you can examine both of these things independently, okay? So the net force will tell you about the acceleration of the center of mass, or lack thereof. The net torque will tell you about the rest of the object. The rest of the object could angularly accelerate. So remember, that was our two-part goal, which we mentioned back when we were introducing center of mass, right? And we're there now. So first of all, the old stuff, our old physics tells us about the center of mass, and our new physics tells us whether or not the rest of the object does anything. So first we talked about angular kinematics, which was, can we describe that rotation? And now we're talking about torque, which is what leads to the angular acceleration. And in this case, we have a net force that's 0, but a net torque that's not. In fact, these guys are independent. What the center of mass does and what the rest of the object does are independent. It may seem strange that they can be independent when they both use the same raw material for their calculations. They both use the force. But the difference is that when you're just working on net force, you just care about what the forces are. Location doesn't matter, right? It doesn't matter that one force is on one side and the other one's on the other. It just matters that they're opposed, and that's why they cancel. But when you get to the torque side, the fact that one force is going one direction and the other one's going the other direction is also counteracted by the fact that they're on opposite sides of the pivot. Location matters. And so they actually drive rotation in the same direction. Okay? So that's how they can be independent. And so what I want to do is I want to show you, prove to you that they really are independent by doing all of the 4 cases. This is the case where the net force is 0 and the net torque is not. Let me do the opposite case. Case 2, we'll do it like this. Here's our ruler. Now we have a force like this, and we have a force like this. And I've tried to draw them both on the ends. There we go. Oh, and that's a terrible drawing. Let me try it again. Okay, that looks a little bit better. So looking at this, is the net force 0? No. The net force is definitely not 0. In fact, if we were to give it a direction, we might, for instance, go old school here. We might set x and y axes. We might say that that is which way? Negative y direction. So the net force is not 0, and the acceleration of the center of mass is not 0. And they're both in the minus y direction. So if I were to draw the center of mass here, the center of mass is going to have to accelerate accordingly. So this thing, it will move down. It will move forward, I should say, not down. This is the top view, so it's move forward on the horizontal surface. Now that guarantees the center of mass moves in a straight line, so that can't participate in any kind of circling, right? But the rest of the object could still circle around it, so let's check it out. So this force, sketching that around the pivot, right, the center of mass is going to have to be the pivot, because we already know it moves in a straight line, it doesn't go around. What's the direction of that torque?
Positive.
That's counterclockwise or positive. What about the other torque? That one's clockwise. Negative or clockwise. So now they don't reinforce. Even though the forces are in the same direction, they're on opposite sides of the pivot. So they have opposite opinions, right, about which way the thing should rotate. You probably experienced this on a seesaw, which is going to be my next example, right? On a seesaw, both people are getting pulled on in the same direction by the force of gravity. But the reason it can balance is, of course, if one person gets pulled down, that would take the seesaw one way, and if one person gets pulled down, that would rotate the seesaw the other way. If these forces are exactly the same, and they're applied at the same distance, the same orientation and everything, what's the net torque here?
0.
0. Which means that there will be no angular acceleration. Question? No? Okay. So I guess I'll try to demonstrate this. It's hard because the board is vertical, but I'm going to have to hold it up here. Now if I have two forces like this, right, both downward, it causes it to move like this, or I should say forward, right? So if I have two forces that are both forward, it's just going to drive the thing forward, but with no rotation, right? So there's a case where which one is 0 and which one's not is flip-flop, right? Up here, the net force was 0. Here, the net torque was 0. If I just stop with these two cases, you might get the false impression that when one is 0, the other one's not. Of course, they're independent, which means they could both be 0 or neither be 0. Let me do those cases. Let me go to case 3. One, two, three. This one is going to look like this. So what's the net force on that? 0. So the center of mass stays put. Can't accelerate from rest. That really only guarantees, though, that this point here in the middle of the ruler doesn't budge. We still have to evaluate the rest of the object. And now we can see, of course, that this force would try to rotate it one way around that pivot. This one would be the other. And if those forces are exactly the same size, same orientation, same everything, leverage, what's the net torque? 0. So nothing happens. This one's definitely easy to demonstrate. Here I go. Just trying to smush the end of it, okay? I have an up force and a down force in exactly the same location, so nothing happens, right? So there's no action of the center of mass. There's no action of the rest of the object. Everything stays put. And finally, case 4. This is the easiest one to do because I only need a single force. So what's the direction of my net force if I use the x and y axis like this? Negative y. So my net force and my acceleration of my center of mass, they're not 0, they're in the minus y direction. So if I exert a force like this, then the center of mass, this point over here, has to move in a straight line. However, does that force have leverage against that pivot? Yes, it does. Is it in whole or in part tangential to the circle?
In whole.
In whole, yeah. So the net torque and net torque and angular acceleration is in which direction? That would be negative, right?
No, positive.
Positive. Yes, thank you. Remember, the language used for rotational and linear are very different, right? That's why they're not directly comparable, right? These are in the minus x, or this is in the minus y direction. Could be some combination of x and y. Our language for rotational is completely different, counterclockwise or clockwise, right? So here, not only is this thing going to, its center of mass going to move, accelerate from rest, but it's going to also accelerate rotationally. Let me try to demonstrate this. So if I exert a force here, it does both, right? So let me do that again. So if you exert a force on the edge, then you both apply a net force, which makes it accelerate from rest, and you apply a net torque, which will angularly accelerate it and get it rotated. An example that I could also show you is throwing something up in the air. So when you're throwing something up in the air, the force of gravity acts at the center of mass. So it's like acting at the hinge. So what does that mean about the rotation rate in the air? Does it go faster or slower? Or is it the same? It's the same, because there's no net torque on it once it's in the air, right? There's no force has leverage against the pivot. the only force that acts on it is gravity, and gravity acts at the pivot. So that looks like this. When it's flying through the air, the net force is not zero, it's the force of gravity, but the net torque is zero. So the force of gravity acts at the pivot, but it has no leverage. So what you will find is the center of mass will accelerate. Of course, we know what's the acceleration of the center of the mass is what? In flight? G, right? 9.8 meters per second squared. But if the net torque is zero, the angular acceleration is zero, which means the angular velocity is constant. So once it leaves my hand, right? When it's in my hand, by the way, I throw it from the edge, right? So my force is definitely exerting a torque. That's what gives it its angular velocity. But once I release it, there's no net torque on it while it's in the air, so whatever angular velocity it had when it left my hand is there for the duration of the flight, right? Even as the center of mass slows down and stops at the top, it's still spinning. The rest of the object is still spinning at that rate that it left my hand in. Does that make sense? So this was truly supposed to demonstrate how independent these are. If you're working on net force, you're working on what the center of mass does. If you're working on net torque, it's about what does the rest of the object do. Okay? Any questions on that one? Okay, so the next order of business, this is of course highly conceptual. Let's do something with the numbers. We just developed this nice torque equation, so let's use it. So this is my example number 2 with numbers, and I'm going to have a seesaw. I mentioned I would do a seesaw example. Here it is. So a seesaw is this plank. It has this kind of pivot in the middle. Unless you have some weird seesaw, it pivots exactly in the middle. And let me, just to make my life easier, I'll make the plank itself massless. So the plank is approximately 0 kilograms. It's a very light plank. So let's start off slow here. I'm going to have 2 point masses to represent 2 people. I'll call this M1. M1 is going to be 2 kilograms. Now that's a tiny person, obviously. That's impossibly small for a person. But let's make the numbers nice to work with. Let me say that that person sits 3 meters from the pivot, and they want a seesaw with another person who's 4 kilograms. And again, that's not a mass for a person, but it's nice to talk in tangible terms. Now, when you're trying to seesaw with someone, you obviously want to balance out. So what I want to ask is basically, where do I have to put this person so the system balances? Now, if you've ever seesawed with a little kid, you already kind of conceptually know the answer. Do you need to sit on the end here? No. No, where do you sit? Somewhere a little closer, right? So I want to know this distance. In fact, you might say, if you're twice as massive, which you are, right? 4 kilograms versus 2 kilograms. If you're twice as massive, don't you just sit half the distance? 1.5 meters? You're totally right. That is absolutely correct. We will show that because this is twice the mass, the leverage has to be half. So before we can fly and do more complex problems where the answer isn't obvious. Let's just do a simple one where we kind of know what intuitively to expect, okay? So, let's tackle this one, see where we get. I think we can finish this one, and then we'll do a much more complicated one starting next lecture. So I should mention that because you have a single support force, right, the whole system is being held up by that like triangle right there, that's seesaw support. If you have a single support force, you have access to a method, an older method, that doesn't even require torque. And that is what we call the balance method. You guys remember the balance method for finding center of mass? Right? You have to slide your finger along, and where it balances, that's the center of mass. So if this system is going to balance, where's the center of mass? It's right there. The center of, if you only have a single support force, that single support force must be at the center of mass. So you can try it this way. Because you have a single support force, you can do it like this. In fact, you already did this problem. Well, I don't know, maybe you're still finishing out homework 8, but the grocery basket problem, right? You had the cereal, 2 boxes of cereal and the milk. And you had to figure out where do you have to put the milk so the center of mass ends up in the middle of the basket. Why do you want the center of mass in the middle of the basket anyway? What's at the middle of the basket? The handle. So you have your single support force, right? That's where you want the center of mass, right? If you put all your groceries in one end of the basket's tilting over, right? By the way, most baskets don't have just one handle these days, because if the groceries are even slightly asymmetric, it would flop over. What do they have? They have 2 handles, right? And the 2 handles kind of, you hold them together, but then they come to the grocery basket like this, right? So as long as your center of mass of your groceries is somewhere between those 2 supports, they're being supported. It doesn't matter where between the 2, it's just somewhere between the 2. That's going to cause problems later where if we have more than one support force, then you can't nail down where the center of mass has to be. It has to be just somewhere between the 2 supports. That's why I keep on harping on a single support force. Then you know center of mass exactly where it is. So I would welcome you to do this, and you will find that x2, I mean it depends on where you set the origin. I would probably set the origin to be here. And the reason why is because all of my distances are either given or asked for from there. Well, what did I put in for x1? -3, right? What did I put in for xcom? 0, because I purposely put the origin there. I solve for x2, and you would get x2 equals plus 1.5 meters. No big surprise. So we could do this with the old method because we got lucky and that it had a single support force. But let's learn how to do it with the torque method. So the torque method, we can have a number of torques that act on a system. And if there's anything left over, it will angularly accelerate. But of course now, we want to make sure that it doesn't. We want to make sure the system balances. So if there's no net torque, then we don't have to worry about I either, which we have no idea about yet. Doesn't matter what I is. I is the resistance to rotation, rotational change, but we're not trying to make any. We're just trying to keep the system balanced. So let's take a look. I'm going to go over here and check out why is the seesaw not tilting. So this system right here, I'm going to kind of pretend that's my rotational system, right? That's the thing that tilts or doesn't tilt together, right? So I'll call this my rotational system. And I'm going to take a look at what things from the outside world would want it to rotate. Things that act on it from the outside world, well, the force of gravity pulls here. I'll call that Fg1. The force of gravity pulls here. I'll call that Fg2. And of course, for full disclosure, that's not it. That's not the only two forces that act on the system, because if they were, the thing would be in free fall. There's one more force, and that's of course the support force. And that comes from the triangle, so it's above the triangle. So if I wanted to, I could of course write down my net force equation. I might say F net y equals m8y. So I'd set the y direction like this. Of course, I know that the center of mass doesn't accelerate, so yada, 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 I'd find that the support force has to support the weight of both things, right? Now, that's not going to get me anywhere, though, because, of course, there is nowhere in any of the force equations mentioned distance. And that's because for forces, they don't care. Forces don't care where they're applied. It doesn't matter that one's on the left end, one's over on the right, and one's in the middle. There's just no mention of that at all. You're going to have to use torque. Okay? So let's do that. I have a pivot, which is fairly straightforward. On a seesaw, of course, there's a kind of a well-defined pivot. We'll find that pivoting on systems that aren't supposed to rotate is a little more complicated. So we're going to discuss pivot a lot in the next example. But for now, we just take a look at this pivot, and then we say our three torques, torque of gravity 1 plus torque of gravity 2 plus torque due to the normal force has to all go to 0. Now the torque due to the normal force is really easy, because the normal force acts at the hinge, right? So how much torque is that going to exert? What happens when you try to push on a door hinge? 0. Nothing happens. You have no leverage. R equals 0. Nothing happens. Rotationally, that force doesn't matter. Any forces that act on the hinge aren't going to make the thing rotate one way or the other. Let's take a look at the other two. This force would like it to rotate around the hinge this way. Is that a plus or minus torque? Plus, right? Counterclockwise. If that had its way, the thing would flop down to the ground. That person would flop down to the ground, which would be a counterclockwise rotation of the seesaw, right? Let's take a look at the other one. This one, if it was up to that alone, that person would fall down to the ground, and it would result in a clockwise rotation. So this would be a minus torque, clockwise. So we already know the signs of those two, right? And you had better get some mix of plus and minus torques, because that's the only way you could get 0, right? You have to have that some forces want the system to rotate one way, some want it to rotate the other. So this torque is going to be plus, we decided, and this is going to be minus. And then this one is 0 in and of its own right. The other thing, just to cut to the chase, these are both, the sine of theta term goes to 1, right? These are both applied 90 degrees. Both of these forces are applied completely tangentially, right? So the sine of theta term goes to 1 for both of the first two torques. So for torques gravity 1 and gravity 2. So let's solve this here. Here's what we get. This is probably the single biggest equation where it's easy to see why you can seesaw. If you had to seesaw with a little kid and your forces had to balance, that would never work. You weigh more than the kid, always, right? But in a rotational system, what has to balance is torques. So if one of these, the force is larger, if you weigh more than they do, you can compensate for that by sitting closer to the pivot, right? So the torques have to balance. So if you solve here, you can get, plugging in mg you get that the product of your mass times your leverage has to be equal, and plugging in the values, we have a 3 meter leverage for a 2 kilogram force, or a 2 kilogram mass rather. And then, since the other mass is twice as much, we can solve for R2 is 1.5 meters. And we get the same answer as the other approach. Okay, so that's it for today. We'll pick up a more difficult example of this on our next lecture.